Finite element analysis of transverse beams. At the end of this section, you should be able to create the local and global stiffness and mass matrices for transverse vibration problems. You should be able to apply homogeneous boundary conditions to enforce zero displacements and zero slopes in the model. You should be able to find the natural frequencies and show convergence as we add more elements to our model. And finally, you should be able to solve for the displacements in autonomous systems. We'll begin by deriving our local mass and stiffness matrices. So we're going to have a different model for our element than we had for the axial problems because we have a different form of motion. So here we have one element and we see what's happening to a node on its left side and to a node or a joint on its right side. We have the same rules we had for axial FEA. Every element has to have one material and one cross-sectional area. So within this element, rho, A, I, and E are all going to be constant. And conceivably, we could have loading on here, but we're really going to concentrate on autonomous systems. Now, one difference we're going to see is that each node is going to actually have 2 degrees of freedom attached to it. So in this problem, we have this W1, which is going to be the vertical displacement of that left node, and then W2 is going to be the angle of that left node in radians. And then at node 2, or the right node, we're going to have W3 is its vertical displacement, and W4 is going to be its angular displacement. So each element is going to have 2 degrees of freedom on its left node and 2 on its right node. We're also going to have a different shape function than we saw for the axial problems. And I won't get into detail of where this shape function is coming from, but its form is coming from static beam deflection that applies continuous boundary conditions. The textbook has more detail of where this shape function is coming from. However, for different types of problems, you might want to use different shape functions. And as we'll see, by using a different shape function that maybe is better if you have maybe plastic deformation in your material or in your system, or if you have a nonlinear material, a different shape function might be more appropriate. But we're going to go with this shape function that's generally good if you have materials staying in the linear elastic region of deflection. So starting with the local mass matrix, as we did with the axial, we want to find the total kinetic energy in this element, because what we're trying to do is describe the motion of the entire element by only using the W1, 2, 3, and 4, and that's what this shape function is doing kind of this interpolation of what's happening in between the 2 nodes of the element if all we know is what's happening at the nodes themselves. So what's the total kinetic energy in this element? Well, it's still going to be mass times acceleration. And what we're going to do is we're going to integrate it from the left side to the right side. So we want to take our shape function and take its time derivative, and that's going to give us the velocity. So this is our mv squared with the 1/2 out in front. Rho is going to be our volumetric density. A times dx is going to be our volume, giving us our mass, and then our velocity is going to be that vertical positions squared. Now this is taking into account all the types of positions, angular and translational, when we're coming up with that kinetic energy. But this W is indeed going to be the motion of the entirety of the element. So what we can do is we can do this integration. We can substitute in this definition of W into the integral. And what's going to happen is we're going to get a fairly long solution to that integral, which we're going to be able to put into matrix form. The details of this are in the attached Mathematica file. But we're going to be able to express it as 1/2 W dot transpose times M, the local mass matrix, times the W dot. W dot being W1 dot, W2 dot, W3 dot, W4 dot in this example, but it's going to be local to whatever element we're talking about. So it's the 4 degrees of freedom that are attached to our element. So notice that the local mass matrix is 4 by 4 now for each of our elements because we have 4 degrees of freedom attached to each of them. So, and the mass matrix becomes a little bit more complex than what we saw in the axial problems, that L, the length of each of our elements, is going to come into play inside the mass matrix. But coming from the derivation, as long as we are okay with the shape function we're using, as long as it's appropriate to the material and to the structure we're analyzing, this is going to be our local mass matrix. So we can compute each element's local mass matrix based on its density, its area, and the length of each individual element. So we'll put that aside and we can go on to our local stiffness matrix. We're going to use that same shape function as long as it's appropriate to the material that we are analyzing. And now, like we saw with the axial, for the stiffness, we want to look at the total potential energy in each of our elements. So in this element, we're going to use 1/2 times its strain energy, but the strain energy is now for a transverse object rather than an axial object that we saw before. So for the potential energy, the strain energy is going to be EI times this second derivative of our position with respect to x squared. So what we can do is we can take our shape function, we can put it in here, take its second derivative with respect to x, and we can complete this integral. And once again, we're going to get a pretty long expression for that that's in also the Mathematica file. But what's going to come out in the end is we're going to be able to write that instead of a scalar equation in a matrix form. So we can say that the V is 1/2 times our 4 by 1 transpose of our positions, and then times our local stiffness matrix K as defined to the right. And here, each of our local stiffness matrices is going to be dependent on that element's Young's modulus, that element's area moment of inertia, I, and the length of that individual element. And this too is a 4 by 4 matrix as it's going to apply to the 4 degrees of freedom that are attached to each element as we calculate it from left to right in our beam.